This next lecture is bound to another category of operators which is very useful in normed vector spaces. So they are called conjugate operators, or the conjugate of an operator. So as we did before, let x and y be two normed vector spaces. Okay, so recall that L of xy stands for the linear operators defined from x to y, and B of xy are the bounded linear operators or continuous linear operators from x to y. So we have seen them before. Now let A belong to L of xy. So A is a linear operator. Okay, and now let x star, y star be their duals of x and y respectively. Let y star belongs to y star. So this is a continuous linear functional. It goes from y to r. So now if we take y star composed with A, it goes from x into r. So clearly, y star composed with A belongs to L of xr. So it is a linear function on x, but what's lacking is to be in the dual to be continuous. So for that we assume that A is continuous. So assume A is bounded. So this tells us, of course, that A belongs to B of xy. So it's a bounded linear operator. Then in this case, okay, then y star composed with A is continuous. And that was lacking, okay, to claim that y star composed with A belongs to dual space x star. So now what we have a map that goes from y star into x star such that the little y star gives us y star composed with A. So this gives us a map, and it's very easy because of the linearity of A that this operator, okay, let's give it a name just for the sake of, let's call it capital T for the time being, okay, capital T for the time being. So it's easy to see that T is linear. Okay, it's linear. And using the properties of the norm of operators, we see that the norm of y star composed with A is less than the norm of y star times the norm of A, so T is bounded. Okay? And norm of this operator is less than the norm of A. So we have definition and notation. Okay? The operator T is called the adjoint of A, the adjoint of A, and will be denoted from now on by A star. So T, instead of T, we'll write A star. Okay? So again, if A belongs to B of xy, then A star belongs to bounded linear operators from Y star to X star, and the norm of A star is less or equal than the norm of A. So that's what we saw just before. Okay, we saw that the adjoint is a bounded linear operator between the dual of Y to the dual of X, and that the norm of this operator is less or equal than the norm of the original operator A. Okay, so we have the following result, theorem. Okay, assuming all the assumptions, let X, Y, and A be as before. So we're assuming that A is a bounded linear operator. Then the adjoint, in fact, has the same norm as A. It's amazing. Okay? Okay? Preserves the norm. So okay? Prove. We know that the norm of A star is less or equal than A. So let's for any X, we know that for any X in X, there exists a Y star in Y star, oh, in X star, norm of Y star equals to 1, such that Y star of A of X gives me the norm of A of X. Okay, because A of X is a vector in Y. Okay, that's why we can always achieve that. It's the Banach theorem. So now, what do we have? Y star of A of X, that is Y star composed with A of X, and that is A star by definition of Y star of X. Okay, remember that A star Y star belongs to X star, the dual of X. So that's why it does make sense. A star Y star of X. This is a real number. So we have now that absolute value of A star Y star of X. This is less or equal than the norm of A star Y star, norm of X. Okay? And this tells us, okay, this is less or equal norm of A star, norm of Y star, norm of X. Okay? So this is just the definition of the linear operator A star with its norm, but we know that the norm of Y star is 1, so this is just the norm of A star, norm of X. Okay? And since A star of Y star X is Y star of A of X, which is equal to the norm of AX, so we get that the norm of A of X is less than norm of A star, norm of X, and this is true for every X, for any X in X. So by definition of the norm operator of A is less or equal than the norm of A star. So these two operators do have the same norm, and that's what we claim. But here we have a little bit more. I want to go back to what we wrote just here. This here is very interesting. Okay? So again, let me rewrite it here. So let me rewrite it, remark. So we have A goes from X into Y, A star goes from Y star into X star. So A star of Y star, that is Y star composed with A. This is very important. Okay? So in particular, for any X in X, we have A star Y star of X is equal to Y star A of X, which is Y star of A of X. And if you write the value for linear fractions, we use this. So we have A star of Y star of X is equal to Y star taken A of X. Okay. This, of course, is very useful when we deal with Hilbert spaces. So this will be very interesting. Okay. Great. Some basic properties. So here, basic properties of the adjoint. Okay. So we have theorem. Let X and Y be two normed vector spaces. Okay. Let A and B in B of xy, meaning linear operators. Then we have number one. If you take alpha A conjugate, you get alpha A conjugate for any alpha in R. Okay, if you have a complex vector space, the scalars are complex, then you have there the conjugate of alpha. Okay, the conjugate of alpha as a complex number. Okay, 2, if you take A plus B as a linear operator, you will find A star plus B star. Okay, the last property concerns the composition. How does the adjoint behave with respect to the... So this is how it goes. Now let C belongs to bounded operators from Y to Z, where Z is a normed vector space. Then now we can consider the composition between C and A. So we have C composed with A star is equal to A star composed with C star. Okay? Very interesting. Okay? Remark. So these are just the properties of remark here. If you take the identity map, if Ix is the identity map, linear map, okay, of X, okay, then the conjugate of the identity map is the conjugate of the X star. Okay, so Ix conjugate is just the identity map of X star. Okay, great. So now one final property, which is about the inverse. What happened to this one? So theorem. Okay, let X and Y be two normed vector spaces. Let A be a bounded linear operator. And we assume that we have an inverse, okay? So assume that A inverse exists and is continuous from y into x, assume that, then the A inverse adjoint, okay, is in fact the inverse of the adjoint. So the adjoint has an inverse, and it is the adjoint of the inverse of A. Okay, so proof. Okay. From our assumptions, we know that A inverse adjoint, okay, exists from all what we discussed today, and A inverse adjoint belongs to B and has the same norm as A inverse, okay, from X star into Y star. Okay, so now let X star belongs to X star. Okay. Okay. So now let us take A star composed with A inverse star of X star. Okay. So this one we have to be very careful. Huh? We are very careful here. Okay. Let me just say something before I proceed. Okay. So this operator here goes from X star into Y star. This operator here goes from Y star into X star. So when I compose the two, I will be going from X star into X star. Okay? So that's why I'm taking X star in X star. Okay? So we are defined on capital X star, the dual of X. Okay? So this is equal to A star of A inverse star of X star. Okay? So by definition, this is A star of X star composed with A inverse. Okay? And finally, the definition of A star, the adjoint of A, this is X star composed with A inverse composed with A, which is X star composed with I of X, and this is exactly X star. And the same ideas will apply, okay, that for any Y star in Y star, okay, we have A inverse star composed with A star of Y star equals to Y star. Okay, so what does that mean? It means that these two operators, okay, so basically that's what it means. It means that A star composed with A inverse star equal I of X star, and A inverse star composed with A star equals I of Y star. Okay? And this implies what? It implies that so A star is invertible, okay, and A star inverse is equal to A inverse star. So it is invertible, and its inverse is in fact the adjoint of the inverse of A, which is then continuous abounded operator. So this takes care of the inverse. Now, some of the results we are going to be discussing next are a little bit more complicated, and so these are all basic results that we have seen. So now we go for a beautiful result discovered by Schauder. Okay, the following result was discovered by Schauder, the same Schauder that gave his name to the Schauder basis. So we get theorem, okay, let x and y be, as usual, be two normed vector spaces, okay, if A of x to y is a compact linear operator, okay, then A star, the adjoint, is also a compact operator. Okay. What about the converse? What if the adjoint is compact? For that we need to have some kind of completeness. Okay, so if Y is a Banach space, then the converse is true. It's a Banach space, then A star compact will imply that A is compact. Proof. Assume A is compact. Okay. So in order to prove that A star is compact, we're going to prove that in order to prove that A star is compact, okay, let us prove that every bound sequence for, let us prove, okay, let us prove that for any bounded sequence y star n in y star, okay, the sequence A star y n star, okay, has a convergent subsequence, has a convergent subsequence in x star. Okay. Now let B1 be the closed unit ball of X. Okay. Since A is compact, okay, then K equals A of B1 star closure is compact in Y. Okay? Good. Now, for each n, okay, Yn star is a continuous linear function defined on the entire space Y, in particular in K. So this, of course, belongs to the continuous functions from K into R. So K is compact, and these are continuous functions on K. So you see what I'm trying to do here. What I'm trying to do is to I'm trying to use Ascoli-Arcela theorem here, so that's why we have this family of continuous functions defined on this compact set K, and what happened is for any y in K, okay, the sequence yn star of y is bounded in R. Okay, because the yn stars are all bounded sequence, so here we're using the boundedness, okay? So it's relatively compact. So yn star of y is relatively compact. Okay? And of course they are all efficient maps, okay, because they are linear functionals, they are bounded. So if we take sup, if you set M to be the sup, the norm of the yn stars, then all of them are Lipschitzian. Okay, so we have yn star y1 minus yn star y2 absolute value, where y1 and y2 are in K, is less or equal than m here, the norm of y1 minus y2. So you see, since they are all efficient of the same constant, then we get that the family here, y star and are equicontinuous in C of KR. Okay, so this clearly implies what? That the family is relatively compact, which means that there is a subsequence which converges. Okay, so in particular, there exists. Okay, so Ascoli-Arcela theorem implies that a subsequence y phi of n is convergent. Okay, so there exists a subsequence which is convergent. In particular, it is Cauchy. Okay, which implies that y star phi of n is Cauchy. Okay. In C of K R. Okay? So here, let x belongs to B1. Okay? So A of x belongs to K. Okay? And this implies, so if we take y star phi of n of A of x is Cauchy in R. So limit, okay, limit y star phi of n A of x equals L of x, so n goes to infinity, exists. Okay? So using the linearity of A and yn stars, we see that L in fact is a linear functional defined on X. Okay? Moreover, okay, we have absolute value of L of x is less or equal than sup the norms of the y star phi of n, okay, norm of A of x, okay, which implies that absolute value L of x is less or equal than the sup of, because they're all bounded, norm of A, because norm of x is less than 1. So this L here, this linear functional, is in fact, okay, in the dual space. So it's a continuous linear functional. So let us write L equal x star, okay? So now, since y star phi of n is Cauchy in C of kr, this tells us that by definition, for every epsilon, there exists n0 such that greater than 1, such that for every n and m greater than n0, the sup, because this is of course defined on ck of r, sup of y star phi of n, a of x, minus y star phi of m, a of x, less than epsilon, where x belongs to B1. So remember, that k is the closure of a of x, so the sup norm, that's exactly what it leads to, okay? So in particular, this tells us that for every x in B1, we have y star phi of n, a of x, minus y star phi of m, a of x, less than epsilon. So if we let m go to infinity, let m goes to infinity, we get that y star phi of n, a of x, minus x star, this is less than epsilon. And this is true for every, I'm sorry, x star of x, okay? So this is true for every x in the unit ball, and in particular, so by definition of the adjoint, so what we have here, for every x in B1, okay, we have a star of y star phi of n at x minus x star of x less than epsilon, or the norm, because we can take the sup over the unit ball, a star y star phi of n minus x star less than epsilon. So for every epsilon, there is n0, such that for every n bigger than n0, we have this. So, okay, limit a star y star phi of n is equal to x star when n goes to infinity, and this is in the strong convergence in x star. So what happened is, Ascoli-Arcelin is at the heart of this proof, okay, to prove that indeed, if A is compact, then A star is compact. Now the second part, we assume that Y is a Banach space, the converse, what happened to the converse, okay, so assume Y is a Banach space. Okay, and okay, assume that A star going from X star to Y star, so from Y star to X star, is compact. Okay, then A double star, meaning the conjugate of the conjugate, which goes from X double star to Y double star, the bidual of X and Y, is compact. This is coming from the first part. So we go to the dual of the dual, so that's the bidual. Okay? So next, then if x belongs to x, so this we can see it as an element of the bidual, and we have a double star of x. Okay? This would be an element of y double star. So we take now going to be defined so it's an element of y double star. So if we take the dual of y star, so if I take this, then this is a real number. So this is equal to what? So this is by definition of the conjugate of a star. So this is x seen as an element of the bidual composed with a star at y star. Okay, so I'm looking at x as an element of the bidual of x, okay, x double star, which is x of a star y star. Okay, and remember x is an element of the bidual, so the bidual, which is the same as from the embedding of x into the bidual of x. And now we use the definition of the conjugate of a. This is y star composed with a at x, which is y star of a of x. Very interesting identity. So here, this implies, okay, so a double star of x, okay, is equal to a of x. It's very interesting because this is a of x is an element of y, so we can embed y again into the y bidual, and this, of course, this here is just a of x as an element of the bidual taken at y star. Since y star was any element in the bidual, okay, so here this y star was arbitrary for any y star in y star. Okay, we have this. Okay, so they are equal here. Okay, good. So if we take now the unit ball, a double star of B1, so a double star of B1, this is equal. Of course, I'm looking at B1, the unit ball of X. So I look at X embedded into X bidual, and then you get this is the same as A of B1. Okay? So now A double star is compact, so A double star B1 closure where in the bidual, closure in the bidual, this is compact. Okay? Is compact. In X double star. Okay? So A B1 is totally bounded. This is what I wanted to get to. It's totally bounded in Y. Okay? Hold on. A double star. What did we say about A double star? Where does it go? A double star goes to Y double star. Sorry. This is in Y double star, not in X double star. Okay, so now it's totally bounded in Y, because A of B1 goes inside Y. Since Y is a Banach space, this is where we use now, okay, it's a Banach space, okay, then the closure in Y, so A of B1 closure in Y is totally bounded and complete. Therefore, A B1 is compact in Y. So, very interesting how to see how we can get this property. We have to be extremely careful. Of course, if y is reflexive, then y double star is equal to y, and therefore the conclusion is obvious that the compactness of A star will imply the compactness of A. Okay, so let X be a normed vector space. Okay, next let X be a normed vector space. Okay. Okay. So what we're going to do right now is discuss the null space and the range of A double star. That's exactly what we're trying to do, okay? And for that, we need some new properties. So here, so let D be a non-empty subset of X, okay? So we can and D star be a non-empty subset of X star. So we have a non-subset in X and a non-subset of in the dual. Okay. So now set D orthogonal to B. Okay. So these are the elements in the dual such that D is in the null space of X star. So in other words, X star reduced to D is equal to 0. Okay, so X star is equal to 0. Okay, and the annihilator of D star, annihilator or orthogonal, we use both words in fact, is the element in X such that X star of X equals 0 for any X star in D star. So it's easy to see that D star orthogonal is the intersection of the null space of all the X stars in D star. Okay, so that's the definition. Okay, we call them orthogonal or annihilators. Okay, it is very easy to check that D orthogonal and D star orthogonal as well are linear subspaces which are closed. Okay. Okay. Good. So now these operations can be extended, and this is how it goes. So we can define now D orthogonal. We are in the dual space of X, and then take the orthogonal back to X. So this is in X, and the same goes for D star. First orthogonal takes us to X, and then if we take orthogonal, here we go to X star. Okay, so these are subspaces, closed subspaces. So what are these subspaces? What is the relationship between them and the original set D? So we have the following theorem. Okay, we have, under the assumptions above, we have D orthogonal complement, is equal to the span, because it's subspace, of D closure, because they have to be closed. See? Very interesting. Okay? Okay. Proof. Okay. It is easy to check that D is a subspace of D orthogonal. Okay, that's very easy. So now, okay, and since of course D orthogonal is a closed subspace of X, then the span closure of D will be a subspace of D orthogonal. Okay, so now assume, okay, let us assume that the span closure of D is different from D orthogonal. Okay, let X0 belongs to D orthogonal, but not in the span. Okay, so then distance from X0 to the span of D will be equal to delta positive. Okay, so I'm gonna tell us what separation. There exists X0 star in the dual space such that X0 star of X0 equal delta, and that the hyperplane defined the new space by X0 star contains the span, and the span of D is in the null space of X0 star. Okay? So in particular, we have D, which is in the null space of X0 star. Okay? So X0 star belongs to D orthogonal. Okay? Okay? But because X0 star of X0 is equal to delta not equal to 0, then X0 does not belong to the orthogonal contradiction. Okay? Okay? So this implies that the span closure of D is equal to D orthogonal. This is very, very important result that we are going to use when we deal with adjoint and spaces. Remark, one will ask, what happened to the subset of the dual space? Okay, so if D star is non-empty subset of A star, okay, then we have span closure of D star is included in D star orthogonal. Okay, so this is true. What is not true is the other way around. Because of the bidual, if you go to the bidual, then it depends if the space is reflexive or not. You see, that's why. So we may not have the equality. In other words, we may not have in general D star orthogonal equal the span of D star. So remember, we went to the dual in order for us to catch this business. So here there may be a problem. Okay. So here, if the space is reflexive, the equality holds if X is reflexive. Okay, that's basically the conclusion in the previous theorem. The previous theorem would tell us the equality when X is reflexive. So what happens when X is not reflexive? Okay, so let's take an example. Okay, let X be non-reflexive. So we can take C0, we can take L1. Well, we have seen the examples of dual spaces, that these spaces are not reflexive. Okay, so now look at X as a subset of X double star. So we have X is a subset of X double star and X double star different from X. Okay, great. So now let us look at now X orthogonal where? In X star. This is in X star. Okay? So very easy to see that X orthogonal is 0 in X star. Okay? Which is the definition of the dual. If you are orthogonal to the entire space, if any function, any element that is equal to 0 on X is equal to 0 everywhere, therefore it's equal to 0. Okay? And now, if you take X orthogonal here, so this is 0 orthogonal in the bidual, and that is X double star. Okay? Great. So, but X is a closed subspace of X double star, so we know that since X, it's a Banach space. Sorry, I forgot. So we have to assume that X is a Banach space. So assume X is a Banach space. Okay. Then the span closure of X is X in X double star. Okay. So here is an example where you have span of X is different from X orthogonal. Okay, so any Banach space which is not reflexive will lead to an example of this. So the theorem is not valid all the time. Okay, the previous theorem. Okay, so now more properties of these two spaces. Okay, more properties. Okay, we have for any non-empty subset D of X, we have D bar orthogonal is the same as D orthogonal. Okay? And the same holds in D star for any non-empty subset D star of X star. We have okay, D star bar orthogonal is the same as, so whether you take the closure or you take the subspace, you get the same orthogonal set or annihilator of the set. Okay? For now, we are ready to prove a beautiful theorem. Okay? And connect all this to the adjoint now. Theorem. Okay? Let X and Y be two normed vector spaces. Okay? Let A be a bounded linear operators from X to Y. Okay? Then we have the following is true. Number one, the range of A orthogonal is equal to the null space of A star with adjoint. Two, the range of A star orthogonal, so this is we're in the dual space now, so I came back to the space, is the null space of A. Great. And finally, three, the closure of R of A is equal to the null space orthogonal. Beautiful. And this is very, very important theorem for what's coming, for the properties of A and A star. This theorem will be a crucial theorem. So it connects the range and the null space of A with the range and the null space of A star. So proof, let us go over the proof. Proof is straightforward, but let's just do it for the sake of, okay? So let us proof of one, okay? We have Y. So remember, the null space of A star. A star goes from where? It goes from Y star, see, A star goes from Y star into X star. So the null space is in Y star. So let Y star belongs to the null space of A star. Okay? So if and only if A star of Y star is equal to 0. If and only if Y star composed with A is equal to 0. Okay? If and only if for every X in X we have Y star A of X equal to 0, which means that Y star belongs to the range of A orthogonal, because A of X describes the entire range. Okay? So you see, this tells us, since we did if and only if, so N of A star is equal to R of A orthogonal. Now, proof of 2. Proof of 2. We have X belongs to N of A if and only if A of X equals to 0. And this is true using the duality between Y and Y star. So A of X is a vector in Y. So this vector is equal to 0 if and only if for every Y star in capital Y star, we have Y star of A of X equals 0. And this tells us that if and only if for every Y star in Y star, we have Y star composed with A at X equals 0. If and only if for every Y star in Y star, we have A star of Y star at X equal 0. Okay? So this tells me that X, if and only if X belongs A star Y star for every Y star and Y star describes the range of A star. Okay, so this is the range of A star orthogonal because we're back in space. Okay, so this tells us, of course, once I put everything together, okay, we get that the null space of A is just R of A star orthogonal. Proof of 3 now. Okay, so if we use the previous theorem, we know, so using the previous theorem, we get that we know that R of A is a linear subspace, so the span of R of A is just R of A, but we have the closure, and this is equal to R of A orthogonal, so we are now in Y star, and come back to Y. Okay? That's what it is. And now using property number 1, we know that R of A orthogonal is N A star, okay? And this will be orthogonal. This gives us proof of number 3 and the proof of the theorem. So this is the end of part 1. So next I'm going to be discussing more properties of the adjoint in the second part. Thank you for your attention.